Welcome to this video on sampling distributions and the central limit theorem. In this video, we will answer the following questions. What is a sampling distribution? What is the central limit theorem? And why is the central limit theorem so important? In statistics, one of the first types of probability distributions we encounter is the normal distribution. The distribution of this data is sometimes referred to as the empirical rule, where we memorize sometimes that 68% of our data lies within one standard deviation of the mean, 95% of the data lies within two standard deviations of the mean, and almost all of our data, all but 3% of our data lies within 3 standard deviations of the mean. We then go on to learn about z-scores, and we use either z-tables or software to find the area under the curve for a given z-score. But the question on everyone's mind is why? Why are statistics professors so in love with a normal distribution? Why do we spend so much time on this particular model? So it's true that some populations are normally distributed just naturally. So for example, if I were to graph the height of women, I would get a normal distribution. And then if I graph just the heights of human men in the world, I would also get a normal distribution. But recall, back at the beginning of statistics, we learned about a lot of other ways that data can be distributed. It may be unimodal, but it could be negatively skewed or left skewed, or it could be positively skewed or right skewed. Furthermore, we also learned that data doesn't have to be unimodal. It could be bimodal or multimodal. There's so many different ways that data can be distributed. So then why? Why are we spending so much time on this single way that populations can be distributed? And the answer to that question, quite simply, is the central limit theorem. As you can see here, the central limit theorem is being depicted as a superhero. And that's because the central limit theorem is so powerful. It's really at the heart of inferential statistics. Central limit theorem says, don't worry about the shape of your population distribution. Because, why? Because we can take a set of data that is not normally distributed, as you can see over here, and if we use what's called a sampling distribution with n, our sample size, 30 or more, then we can obtain a normal distribution, even if our population didn't start out looking that way. Hopefully, the question in your mind right now is, great, but what is a sampling distribution? So it's pretty impossible to understand the central limit theorem without understanding what we mean by the phrase sampling distribution. This is a really important concept, so I'm going to spend the next few minutes in this video developing the idea and explaining what a sampling distribution is. So to best explain this, I'm going to use the example of rolling a six-sided die. Theoretically, if I have a fair die, I have an equal chance of rolling a 1, 2, 3, 4, 5, or a 6. There are 6 outcomes, all of which are equally likely. So that means that they all have a probability of 1 over 6, or about 16.7%. Now you can use your imagination and feel that if you were to try to recreate this in real life, roll the die over and over and over again, and every time you roll the die, plot it on a graph, that you would be very easily, over time, it might take 100 or 1,000 rolls, but you can recreate this uniform distribution. Okay, so this is not the sampling distribution that the central limit theorem uses, because as you can see, n is equal to 1. As long as I am only taking a single data point, n equals 1, I'm just going to recreate the shape of the original population. Nothing has changed from the left side to the right side because, again, my sample size is 1. The power of sampling distributions happens when I allow n to be larger than 1, and then instead of graphing individual data points, I graph the average of those data points. So I'll just read this to you. It says, instead of plotting individual data points, or x, we plot the average of a set of data points. We let x bar, that means our sample average, represent the average of the sample size n. So if we do that, then what happens to the shape of our graph? Okay, so for example, let's say I roll the die twice. Maybe the first roll is 2, the second roll is 6. 2 plus 6 is 8. If I take that and divide it by 2, I have an average of 4. So again, I'm not plotting these individual die rolls anymore, I'm plotting averages. So does the shape of my distribution remain uniform or does it change? Well, let's find out. Let's look at the sample space for rolling 2 dice. So obviously n equals 2 is a far cry from n equals 30. However, we can use this for a few reasons. One is that we still see the shape of this normal distribution and the normal curve emerge even with n equals 2 because we're using what is a theoretical probability distribution. I'm not actually rolling dice. I'm just calculating the theoretical distribution of each of these outcomes. So let's look at our sample space. Remember, a sample space is a complete set of all possible outcomes. Okay, also note that, for example, rolling a 1 and then a 2 is considered a different outcome from rolling a 2 and then a 1. So when we create our sample space, the order of our events matters. So let's try to figure out the probability of getting an average of 1. So what that would mean is that I get a 1 and then a 1. So 1 plus 1 is 2. Right? Remember, to find the average of a set of numbers, you add them all up and divide by the number of data points you have, in this case just 2. 2 over 2 is 1. So as you can see here, there is only one way that I can obtain an average of 1, giving me a probability, theoretically, of 1 over 36, or about 3%. What if I wanted an average of 1.5? Well, how could that occur? Well, that means that these two numbers, they have to add up, and then when I divide by 2, that gives me 1.5. So I could solve for x plus y, as you can see here, and when I do that, that means that the sum of my dice have to be equal to 3. How many ways are there that this can add up to 3? Well, as you can see here, there's only 2 ways that the sum can be 3. So that gives us a probability of about 2 over 36, which is about 6%. As you can see, our probabilities are increasing. Let's keep going. What about the average of 2? So there's several ways that this can happen. We could have a 1 and then a 3. We could have a 2 and a 2. Or we could have a 3 and then a 1. So as you can see, we have a probability of 3 over 36 for this outcome, or about 8%. As we keep going along, looking at finding an average of 2.5, there are 4 different ways this can occur, which gives us 4 out of 36, or about 11% probability of getting an average of 2.5. What about an average of 3? So there are, as you can see, 5 different ways that we can have a sum of 6, which would give us an average of 3. So that probability is 5 over 36, or about 14%. Okay, the most likely outcome is a sum of 7, which you might know if you like to play dice games. So there are 6 different ways that we can get a sum of 7, which gives us an average of 3.5. So that gives us a probability of about 17%. As we move forward from an average of 3.5 to an average of 4, we're going to find that the probability now starts to decrease again. For example, if I want a sum of 8, or an average of 4, there's only 5 different ways that can occur, which is, again, about 14%. So we're kind of going backwards. We're decreasing in probability again. Again, if we want an average of 4.5, there are only 4 different ways that we can get an average of 4.5 or a sum of 9, which gives us a probability of about 11%. Okay, then if we want a sum of 10 or an average of 5, there are 3 different ways that can occur. To get a sum of 11 or an average of 5.5, there are only 2 ways that can occur, which gives us a probability of 6%. And then last but not least, there's only one way we can get an average of 6, which is to roll a 6 and then another 6. And again, our probability is back down to 3%, which is where we started. So let's graph these theoretical probabilities and see what emerges. So here we go. So this is actually a frequency. This is not relative frequency. So we're literally graphing the fact that there's one way to roll a 1, there's 2 ways to roll a 1.5, and so on and so forth. So what does this curve look like to you? If you said it looks like a normal distribution, you are absolutely right. So just by looking at n equals 2 in this particular example, we can see how by taking averages, our extreme values, for example, rolling a 1 or a 6, become less likely, and our central values, maybe rolling averages that are between 3 and 4, are much more likely. So let's look at what happens when n increases beyond 2. So for example, let's say if I have a sample size of 3 and I want to get an average of 1. Well, that means I have to roll 3 ones in a row, so the probability of that is much less. It's only 1 over 216. If I have a sample size of 4, then I'd have to roll 4 ones in a row, which is 1 over 1296. That's the probability of getting 4 ones in a row. And as you can see, once we reach n equals 30, which is what the central limit theorem requires, the theoretical probability of getting 30 ones in a row is almost 0. So what's happening here? What we can see is that when we just are collecting sample sizes of 1, we're just going to end up recreating our population shape. Nothing has changed. However, when we let n be larger than 1, and we start rolling the die and then averaging our dice rolls, then we start to see this normal curve emerge. And that's really, really, really powerful. So let's go back to our central limit theorem and talk about some of the requirements that we have. Again, we have the fact that n has to be larger than 30 or equal to 30. The only exception to this is if you know that your original population data is normally distributed, that n can be any size. So again, the magic of the central limit theorem is happening because we aren't plotting these individual data points anymore. We're plotting these averages of sample size n. So I really like this image here of this normal curve with a bunch of x bars plotted on here, because this really drives home the idea or the concept that we're not graphing x anymore, we're graphing x bar, or the average. As you can see here, the mean of the set of data is going to be the mean of our population. However, the one exception here that does change is that our new standard deviation, the standard deviation of all these sample means, is going to be our population standard deviation divided by the square root of n. So basically, as our sample size increases, the width of our distribution is going to shrink. So here's the requirements that we have of our central limit theorem. The population has to have a well-defined mean and standard deviation. Does that mean that it has to be normally distributed? No, we simply have to know its mean and standard deviation. It does not have to be normally distributed. When we go to create a sampling distribution, we need to have random independent samples, and those samples have to comprise less than 10% of the population if we are to treat them as independent. And then lastly, as I've mentioned several times in this video, our sample size has to be 30 or more. I hope this video has helped you to understand sampling distributions and the central limit theorem better. Have a great day.